Alrighty, just to finish up what we were talking about yesterday, that I was looking at a component here which produces a multiple set of arrival events, each with their own index, and with a state variable that keeps track of the number of arrivals of each of the different ones. And noted that it was a combination of two patterns that we've seen. One, the arrival process pattern, which is characterized by an event which schedules itself after a certain delay. That's one pattern that we've seen repeatedly. Now, it's not universal in that, if you recall from the models that we were looking at where we had a finite calling population, then an arrival process to represent the arrivals in that context is not an appropriate pattern to use. The second piece of this was the for loop pattern, which I traditionally use the name init with an argument. And the difference is that, well, first of all, the for loop pattern executes only a finite number of events, schedules only a finite number of events, unlike the arrival process pattern, which in principle can have an infinite number of events. I mean, or at least it's unlimited. Whereas the for loop pattern is finite, and it's analogous to a for loop in that there's a certain fixed number of times that you have something happen. And that's what a for loop does in every language that's out there. And in event graphs, it is typically represented by an event that has an integer argument that represents the index of the thing that you're doing. It has a self-scheduling edge that passes an increment of that argument, and then also has a condition for the termination, or the condition for stopping the scheduler. So those are the two patterns that this comes together with. And what this does is this therefore produces a stream of a sequence of, in this case, arrival events that have an integer argument. And so any component that has that has an event with an integer argument that would kind of trigger a bunch of things can listen to this and therefore be driven by it. And the example that I gave was the index version of our situation where we had two customer types. So this multi-arrival process was able to produce a sequence of two types of arrival events. That is, in this particular model, we're limited to the two. Now, in principle, you could have more than more than two types of customers, and that would be a slightly different model because, as you see here, when the end service event is scheduling the start service event, you have to take into account what the priorities are. So if you have only two possibilities, the priorities are fairly clear. You know, if you prefer one over the other, then those are the two conditions. If you have three, then it gets a little more complicated, as you might imagine. And four gets yet more complicated. In other words, for every n types of customers, there presumably would be, you would need some kind of rule that would say, if I have this particular set of customers types that I could process next, then which ones should I do? And again, that that absolutely can be done. It's a little more complicated. The point here is that this is how we can drive this component here, because it requires an arrival event with an index, with an argument that's an integer, and here we have a component that produces a stream of those, an unlimited stream. Okay, so that's what we were doing yesterday. Now, moving on to today's agenda, we're going to look into this idea of subcomponents, which is analogous to subclasses in object-oriented programming, as we were talking about. We've seen several examples of this already, and now we're going to delve a little bit more deeply into what that's about. And the example I'm going to be using to illustrate this is the problem one or two assignments ago, where it was a variant of our multiple server queue where instead of customers arriving one at a time, they arrive in batches. Do things like that happen? Well, I mean, if you have a, like a restaurant or something like that, then, you might, a car pulls up and 3 people get out. So an arrival does not cause one more to be in the queue. An arrival would cause however many are in the car to be in the queue. Okay, so that, and the basic multiple server queue, if you recall, had to be tweaked to do that. Okay, so I'm going to look at 3 variants of of how to model that in a different way by reusing our simple server component, in at least 2 of them, and one for the situation where we have entities. In other words, this is what I call the programmer virtue of laziness, where with the multiple server queue pattern, if you will, you have a situation where you've modeled a big piece of what you need to do, but now we're tweaking it. And so you have 2 choices. One is to kind of do it all over from scratch, as I made you do in the assignment. Again, that's just, as the instructor, that's part of my prerogative, I guess. But the thing is that given that we had a simple server component in our hands, what's the minimum amount of work we could do to get the same result? And that's where these subcomponents, which is analogous to subclasses. And if you think of the relationship between event graph components and SimKit, you see that each component is represented as a class in the implementation. So it can be useful to kind of reuse these things through an a framework analogous to inheritance or subclassing. So and I call it a good bang for buck because given what you have already, with a very little amount of work, you can get new features. And so, as opposed to doing everything from scratch, which is a lot of work, or more work than you necessarily need. Okay, so, and when this object-oriented stuff came out, it was, I remember dealing with a lot of models where it was just kind of overused to the, you can overuse this. In other words, at some point it's, they were using inheritance to implement something called polymorphism, which is not the most ideal thing, but that's sort of a different idea. So it can be overused, but if it's underused, then you're doing more work than you have to. Okay, so here are the things to keep in mind. And again, there's a direct analogy between the event graph part of it and how it's implemented. So a subcomponent, what does it have access to? Remember, events have access to only three things. They have access to parameters. Each event has an access to parameters. It has access to state variables, and it has access to whatever arguments are passed to it. Those are the only three things that an event has access to. Now, within an event, as you've seen, you can do the analogous thing of local variables. So, for example, if I have a state variable that's a container for customer entities, and within an event I pop the first one off, it'll usually store that in a local variable. But again, that, as with methods in programming, the local variables, if you will, only have existence for one execution of the event. But they can be used to pass to other things, as we've seen. So similarly, a subcomponent has direct access to all state variables, and that's why in the Java we declare state variables to be protected, so that if you subclass it, then you have direct access to it. That's part of the idea here. And then in the implementation, because parameters are private, you don't have direct access to them, but because you have setters and getters, particularly getters, you do have indirect access to them via the getters. So if in a subclass I needed to use, say, one of the random variates in the superclass, I could simply use the getter for that. Or if I needed to, what's another parameter? Well, in the multiple server queue, one of the parameters we'd have is the total number of servers. And if I need that in a subclass, a subcomponent, then I could access that via the getter. Now, in the event graph, if that's the case, you don't always put the get part in, but that's what's understood. And to represent that, we have a similar notation as with UML. So if I have a superclass, I put it in a box, and then a subclass in a box, and then we have this kind of open arrow that says, in this case, if I have an event graph component and I want to write a subcomponent of that, then I represent it this way. And we'll see some examples of that. Okay, now, in the event graph terminology, then, there are essentially three possible things that could happen when we start to find, what is it that makes a subcomponent? Well, typically, you will have at least one more event. That isn't necessarily the case. We actually saw an example in the where we wanted to change the priority rules for the servers with efficiencies, remember? And there we didn't add any extra events. We just kind of changed the way that the container for the servers was being sorted. But usually in a subcomponent, we're going to do one of several things. One is we would, and we've seen several examples of this, where we augment the superclass event. So we've seen examples where we have an arrival, that we want the arrival to correspond with the arrival process arrival, but we also wanted to, say, create an entity that would be heard by our entity server. So that's augmenting the superclass event. In other words, we want the superclass event to do its thing, but then we want it to do a few more things. And in the implementation, as you saw, what we do there is we actually directly call the superclass method and then add whatever it is that we're adding. In terms of notation, again, just with a regular event, or we may define just a whole new event. And we will also denote that with just sort of the fine circle. Now, we will see some examples of this where we actually want to completely override the superclass event. In other words, we don't want to have anything to do with the superclass event in that particular case. We want to override that, and so we'll denote that with a heavy circle, and that will mean that whatever's happening in the super component is not going to happen. We're going to do something else instead. And then finally, because we're dealing with, because sometimes we may schedule an event that exists in the superclass, the super component, but not in the subcomponent. In other words, we can schedule an event which is defined in the super component, and then we'll denote that with just sort of a little dashed line for it to indicate that we're not defining anything new for it, but that exists in the superclass. Okay, so the example I'm going to use throughout is this batch arrivals model, and it's going to be a simple model. So, but we're going to componentize it. In other words, the problem I asked you to do which was actually before we really delved into components and listening and all that. So that was a complete model. As a component, for these server type models, we will kind of abstract the stream of arrivals by basically taking out. So therefore, we have our usual suspects of parameters, which are the service times and the number of servers, and our usual suspects of state variables, namely the number in the queue and the number of available servers, but then we add a parameter which is going to be the sequence of batch sizes, and calling that B for batch. Okay, so the component type of model for that would look something like this, and this is again, run initializing the state variables, the arrival incrementing by a batch. So this is the arrival of a given batch. Now for this, it just because of a little bit of a peculiarity of some of the discrete random variables that are often used, it seems to be possible. For example, common ones are, say, the binomial distribution or the Poisson distribution. You're familiar with both of those, right? Yeah. Don't want to sort of, for some it's kind of a little PTSD to remember that probability stuff, but okay, these are stochastic models, so we have to deal with that. But if you remember, both the binomial distribution and the Poisson distribution have a non-zero probability of 0 coming up when you generate from it. So it's possible that we get a batch of size 0. So again, that's sort of a possibility. And so therefore, in order to protect our start service event, we need to have kind of add the condition that the queue is bigger than 0. So in other words, if we have an arrival of size 0, then even if a server is available, we can't schedule this, because then that would drive our number in queue negative. So that's just the other. So that was in the pure event graph world, that isn't so much of an issue. We can just insist that our stream of batches has to be 1 or larger. But this piece here, this was kind of the essence of the modeling nugget in that problem, which is that it isn't enough to just increment the queue. So if we get a batch of 3, then we need to keep scheduling a start service even after the first one as long as we have a server available and somebody in the queue. In other words, we keep doing a start service until we run out of customers or we run out of servers. So this piece was kind of the little key here. But if you look at this again, we notice that this self-scheduling edge is the only thing that makes this different from our regular multiple server queue. In other words, when we look at this pattern, with the exception of this self-scheduling edge, it looks like a multiple server queue with two differences. One difference is this self-scheduling edge, and the other is this state transition here. So given that we have a multiple server queue component, then it would make sense, at least, well, it makes sense to me. It may not make sense to you, but you're stuck with me here, so at least for the remainder of the quarter. So it would make sense, and it makes sense to me, that to do the minimum amount of work, why can't we just augment our basic multiple server queue component to add this piece and this piece? And this is how we do it. So here in the super component is our simple server. We've seen lots of examples of that. And now here's the subcomponent that simply adds the things that are different from the simple server. And what is it that was different? What was different was this state transition. That is, instead of adding one, we add the batch. And for start service, the simple server component doesn't keep scheduling the start service because we only got one. We would just, you only ever need one. But here we might need more than one. So notice the arrival is has a heavy border, which means that this arrival is not going to do the superclass one. And we need to do that because our state transition is going to be different. And we don't want the state transition in the simple server component. We want this state transition. So instead of incrementing queue by one, we need to increment it by the batch size. That's completely different. And so we completely override the arrival event in the simple server and change the condition. Now, since we've completely overridden the super component's arrival event, and one of the things it did was schedule the start service, so we need to do that. So whenever you completely override an event, you need to, and there are things in the super component that it does that you do want, then you need to do those down here. So one of the things it did was schedule start service under if there's a server available. Now we're going to keep this idea that if by chance we get a batch of size 0, then we're not going to do that. So we're going to add that condition. But then now, okay, so here's the start service. Now start service has a thin border, which means that it's going to use everything that the start service in the superclass does as well. So what did it do? In the superclass, it subtracted 1 from the number in the queue. It subtracted 1 from the number of available servers and scheduled the end service. So all of that will happen because we have indicated that by our thin border here. But in addition to that, we're going to keep scheduling the start service as long as we have both a server and a customer available. Okay, so now we can just listen to a regular old arrival process because see, we have an arrival event, and if we have one of these guys, then this arrival event is going to be what's executed, not the other one. So this is the listener diagram for that. Is going to be like, let's see, so that is what I'm calling a simple batch server. Let's close all these. Okay, so we're going to extend simple server now. We're not, simple server extends some entity base, so we have all that stuff. We have everything in, we have everything there except now we have this additional parameter, which is going to be the batch size generator. Now, here we're going to define not a random variate, but a discrete random variate. What's the difference? A discrete random variate is a random variate that can also generate integers as well. So like a binomial or a Poisson or Bernoulli or or a custom one where we tell it what the values we generate are and what the probabilities are. So we'll see some examples of that. Pardon me?
0, 1.
Yeah, well, the 0, 1 is Bernoulli, but if we'll see an example where, say, a batch could be, say, 1, 2, 3, or 4, and I'll tell you what the probabilities of that are. So that doesn't have a name. It's just like Poisson or anything like that. Okay, so constructors, we still have to do the constructor business. So now when we're subclassing, we will typically, our master constructor for these, the convention, is that we have all the parameters in the superclass, the superclass, and my convention is to list those first, and then call super with those. But then we have the additional one is that because the discrete random variate that's the batch size generator is the additional one that will set that here. So we've defined this as a parameter, and it has setters and getters as before. And again, with the random variates, this is one exception to where we don't want to use copies of these things. So it's a little bit of a leakage of encapsulation, but for a variety of reasons, we actually don't care about that. Okay, so here's how we will implement. Let's see, where's our model? Okay, so here's our arrival event, which is has a heavy border, which means we are completely overriding it. So we defined do arrival. And so our number in queue, now the discrete random variates have a method called generate int, which, as its name indicates, generates an integer. Instead of, see, the generate method returns a double, but we don't want a double, we want an integer here. So we'll increment it by that. And then, fire our property change, number in queue, so that's the same. And then here's our condition. If we have our number of available servers is bigger than 0, and number in queue is bigger than 0. Now here we've used the getters for that, but we could have directly accessed them. And we schedule our start service. Now for the start service event in the subcomponent, again, it had a thin border, which meant that it was augmenting, and when we augment, the first thing we do is call the super, because we want everything in the super start service event. But then all we do is we just simply schedule ourself as long as the number in queue is bigger than 0 and as long as the number of available servers is bigger than 0. So that implements this condition right here. And we implement the high priority by, and there's a SimKit priority. We want to use the SimKit one, not the other ones. Okay, so let's run. Okay, so how do we execute this? Well, so for our arrival, we need an arrival process, or we need something that's going to produce arrival events. Arrival process is our usual suspect in that. So we'll use our uniform 0.9 to 2.2. Our servers, the service time we're going to be a gamma again. Here we're going to, just with playing around, we need at least, it turns out we need at least 5 servers, and that's one of the things you can get from playing with a model like this. How many servers do I need in order to adequately handle this? If I only have like 1 server, then the queue just blows up. In fact, if I have anything less than 5, it'll get really big. So here are, okay, so here's an example of what I was mentioning. One of the discrete random variates that I can use is something called a discrete integer. And what that requires is I need to give it an array of ints that will be the possible values. In this case, my batch sizes are going to be 1, 2, 3, or 4. And then a double array, which is going to be the frequencies of these. Now, notice I say frequencies instead of probabilities. Just for convenience, the way that this is organized is that I don't have to give the probabilities, because giving probabilities is kind of a pain in the butt. Why? Because probabilities have to sum to 1. And it can be infuriating to try to get everything to sum exactly to 1, especially because of the finite precision of these things. So this allows me to give the relative frequencies of these things, and that's usually what you have. Like, so for example, where might these come from? Well, I might observe my system for a while and just sort of count the number of times I get a batch. So maybe in this case, I observed 10 batch arrivals, and in those, 4 of them had a batch of 1, 3 of them had a batch of 2, 2 had a batch of 3, and 1 had a batch of 4. Now obviously, if I'm doing this for real, I want to do more than 10, but you get the idea. So if I had 4,000 of these and 3,000 of the other and 2,000, I can just give those numbers, and then it'll kind of figure it out. That's one discrete random variate. Another one, of course, is our binomial. So binomial has 2 parameters. One is the n, and the other is the p. So this has a binomial of n of 5 and a p of 0.4. Now the difference here is that, so this will produce batches from 0 through 5. And then here what's commented at, I can also give a Poisson. That's another example. So when I run that, and again, just I have the sim event listener, my server's listening to the arrival process. And so when I run that, it runs fairly. One of the reasons these models with just the integer counts in them, as opposed to the entity ones, is they are blazingly fast. Okay, so this just sort of double check that everything got in there okay. My arrival process, my simple batch server, again, that was the subclass of what I just showed you. So here my batch size, the binomial with these, and then I ran it for 100,000 time units. Okay, so now here I've had 64,000 some arrivals, but notice that I've served quite a few more than that, maybe about twice as many. And then average number in queue and utilization, et cetera. So on the other hand, let me show you what happens if I use the discrete one. Okay, that discrete integer variate, remember I gave it the relative frequencies, and the way that it lists it here is that here are the values, 1, 2, 3, and 4, and it turned the frequencies into probabilities for me. In this case, 0.4, 0.3, 0.2, and 0.1. And I got something kind of similar. The difference is because the batch size had different distribution, it kind of worked out that way. Okay, so and again, here, again, by just overriding these 2 events, and this is hardly anything in terms of number of lines of code, which is kind of one metric that some people use. I think this is a pretty good bang for the buck, in the sense that I've gotten a functionality. In other words, I've gotten this model by just doing this. And that, that's sort of the laziness part. Okay, so it turns out that for batch arrivals, there's another option. The other option is that instead of having the server decide what the batches are, have the arrivals decide what the batches are. So that's a slightly different model. And the way that model looks like is this, is that now we have an arrival event which has an argument. And its argument now is not the index, but the argument is the number of batches. So, or the number of customers in the batch. So now, instead of the start service events sort of spinning, we have the arrival event spinning. So in other words, when one of this arrival shows up, and this is kind of like, sort of like the for loop, and but in the sense that whenever it shows up, we're going to just schedule one start service, but then as long as we have more batches, then we're going to keep scheduling the arrival. So these arrivals are going to kind of keep piling up. So instead of one arrival incrementing the queue by the batch size, we're going to have the arrival incrementing the queue by one, but then scheduling itself again for another arrival corresponding to that second guy in the batch, or the remaining people. So that looks a little bit different. So now, what we're going to do is add this new event, add this arrival event, and that arrival event is now going to have an argument, and it's going to schedule the arrival, but because we're not doing anything more with the arrival here, and the arrival is in the simple server, then this is where the dash thing comes in. In other words, we're scheduling the arrival, but we're not doing anything with it. Okay, we're going to do that only if n is bigger than 0. So that's how we're going to model that. So let's take implemented. So I'm calling it Simple Batch Server 2. Couldn't think of a better name. So now we're not we don't have the batch sizes. So so here's how we do this. So if our batch size is bigger than 0, we schedule another. We schedule the due arrival if the batch size is bigger than 0. In other words, somebody actually showed up, then we're going to do that. Now, if the batch size is bigger than 1, then we're going to schedule another arrival, but counting down. So let's say let's say we get a batch of 1, so this is false, and that's all we do. If we get a batch of 2, now this is true. So we will schedule another arrival, but then we're going to pass it the batch size of 1. Now we will schedule another arrival event, but now 1 is not bigger than 1, and so we don't do it. So if you just put numbers in, you see that kind of works there. So, but now that sort of begs the question of, okay, how do we, where do these guys come from? So that's where we need our basic arrival process. So we need a batch arrival process, I'm calling it a batch arrival process. So, but we're going to pull the same trick on the same trick here. So we're going to have a sub-event component of arrival process, but now we add our parameter b, which is the batch size. So every arrival, we're going to generate the b and pass that to, or schedule an arrival event with that as its argument. And so if we then listen to that with our simple batch server 2, then that will happen. So now in this particular case, because we could hear an arrival event with no arguments, what we want to do is we want to completely override the superclass doArrival event and do nothing. Why? Because the batch arrival process, extending arrival process, okay, now we have the discrete random variate as its parameter. So again, we pass the super classes into arrival time generator. When you see we're subclassing arrival process, and we set the batch generator. So now our arrival event, again, remember it had a thin border, so we do call the super because that's what's going to schedule the new arrivals. Now we're going to generate the batch size and schedule our arrival event passing it the batch size. And basically that's all we need to do. So that when we run that, and again, here we have let's see, I think I wound up with the Poisson here as well. So so here the same, now our arrival process, our batch, what I call batch arrival process, is going to have our intra-arrival time generator and our batch generator. Our server is going to have the same parameters as before. And so when we run that, again, we get something, in this case it was a little bit different because we had a Poisson instead of the other. If we, let's see, just to get the same thing as before, if we run it with our discrete one, then we actually get the same numbers. So again, our batch arrival process has the intra-arrival time generator, the batch size generator, and again, we have a certain number of arrivals, but we have more customers served than that. Okay, so I had one more model to give, and in 4 minutes, I don't think I can get through it. But so we'll have to pick that up tomorrow. So again, just to recap here, we can create subcomponents in a similar manner as we can create subclasses in an object-oriented language. And there's much of the analogies of inheritance in an object-oriented language exist here. And the 3 different possibilities are that we augment our superclass. We've seen that with the start service event in the first model. We can completely override the superclass event, or we can schedule an event in the superclass but not that isn't in the subclass. And we've seen how to implement that. And why do this? Because when we have a component like our simple server, which has been verified, and you no doubt have heard the term VVNA and everything. So okay, so what the first V is verified. In other words, what's verifying is does your model do what it was designed? So if we verified our simple server component in the sense that it does what we have designed it to do, and we have verified the implementation, and one of the things about being able to translate an event graph directly into code is that it's very straightforward to verify that the implementation matches what the event graph said. So we need to verify the design, that is the event graph, and we can verify the implementation. It becomes a very simple matter. Now, validation says, does our component do what we want to do in terms of addressing our problem? And in this case, what has happened is that our simple server component has not been validated for the situation we're looking at. Because in the situation we're looking at, we have these batch arrivals, and the simple server component does not do that. But the batch arrival process does. Okay, but we have a component which has been verified and validated for one circumstance, and now the subcomponent, what we mostly need to do, in other words, verifying and even validating, well, verifying it this way is a lot less work, because we have a verified component and we just need to verify the new stuff that we've done. That's the answer that nobody was asking is why. But I'm sure you're all thinking that. Maybe. Why do this? Because your instructor likes to torture you.